Thank you for joining today. I'm Stephan Sahm. You know me, I'm organizing the Julia User Group Munich. I was there on the JuliaCon in person and also looked up a couple of talks afterwards because I really like to stay up to date with what's happening in Julia. And yeah, last time I did the same. And this time now in an online version, I have a summary for you, kind of what I really liked on JuliaCon. And you see it with the outline. So I have kind of one HTML file. This is actually a markdown under the hood, which I want to look through you with you. And yeah, there are a couple of things, not too much, I think. Let's see. So I'll have kind of 1-2 places where I want to open the video, just because it's great to see moving pictures. But other than that, I did a couple of screenshots and just give you a rough overview. So let's start. My first section is kind of the largest section. It's called a bit from everything, which didn't fit into some other parts. And and the first thing I want to note is kind of that there was a special talk about the history of the Julia repository itself from Christopher Carlson. And that was totally relaxed, just 10 minutes one, and probably even less. And it's just, worth looking at it with some stats about the pull requests and things like that. Made it a little bit funny. But I copied this part out of it, which you probably can generate easily by going to a specific web page. But nevertheless, so this is kind of the, if you want to see kind of how Julia developed, I guess the stars is kind of, the GitHub stars is kind of a nice thing. And this part here, this is 1.0 apparently. And then, the slope definitely increased to what it was before. So it seems to be slowing down a little bit, how many stars get added, but still, it's an impressive part. And his conclusion was that it was, looking back now, it was a good idea to give it a Julia 1.0. So this definitely increased the number of people who collaborated. Because there apparently had been some discussions back then, whether this is a good idea. The next talk I want to mention is the learning jump by example. So I myself not too much into mathematical optimization, but there's this whole ecosystem around jump. And I only took a look in a few talks because for me it's kind of quite unrelated and a bit difficult to appreciate the details. But there was one general talk which I can recommend, Learning Jump by Example, which summarized the different jump optimization problems by having the code to the left, you see it here, and a visualization of the problem to the right. So I really like this format. It's also perfect for doing screenshots. And and one thing which was mentioned also with the Sudoku example is that the current standard solver is apparently the highs. So something like this is always kind of this implicit knowledge. And I was glad to hear this. So apparently if people just want a solver, then they import this highs solver. So jump itself is just an interface, and then you need another solver to actually solve these descriptions. And there were 2 descriptions of the Sudoku. I made screenshots of both of them. The first one you see is kind of using for loops, defining variables in 3 dimensions. And then with for loops, kind of saying that respective dimensions should sum up to 1, so rows or columns. And for the diagonals, you then do kind of this extra to really sum the diagonals. So it's very straightforward, simple. And they showed us a second version, which was not there all along, but meanwhile kind of got there in the feature set of Jump, which uses more complex constraints. And so they are kind of integer based often, but the full list can be found in Jump. So this one now uses a all different constraint. And with this the constraint simplify. So yeah, having this, yeah, you also see kind of a special index syntax. Yeah, the I is going from 1 to 9, and then the I is used to index the X. So with this, we get rid of the for loop, and we get rid of the sum by having this special constraint. There are a couple of more. Yeah, the blocks. Sorry, I was mentioning diagonals. Of course, it's not diagonals where you should have every number once, but blocks. So the blocks are now defined in this way, also very concise. Because this is my only part about jump, I also have a copy of a kind of a summary which was given in this talk about applications of jump. And this was also kind of, it was in general an overview of examples. And it was impressive to see kind of that they are very, very different and going to different fields, also fields where I would think, okay, this sounds like another field, like also differential equations. And yeah, and you see it kind of here, there are tons of applications of these kind of mathematical optimizations. And for me, it's sometimes hard to know kind of, okay, when should I go to the jump ecosystem to solve something like this? And when should I go to yeah, other fields, other optimization libraries, like in the scientific machine learning field, for example? I have still no good answer on this. So I hope the intuition stacks up over time. But it's very impressive to see how many applications they already have covered. Next one is quasi-stable colors. So in general, I always put here a couple of information on top. So this talk is by Mo Kayali, probably I pronounced it wrong, sorry for that. And you find here the pre-talks link. So you should now see this violet thing here on top. So there's always kind of from the JuliaCon, the overview of the talk, where you also find the author again. And then there's a link to YouTube. And this YouTube link is kind of very special in that it refers to a timestamp of the full day. So yeah, if you haven't checked it out, these are recordings from the full day. And hence, yeah, it's a bit difficult to scan them. And most of them, timestamps are provided in a comment, but not on everything. So this is a bit tedious, but at least you have kind of the links over here. And there's also good news that there's a 10th annual JuliaCon playlist, which seems to be in progress. So we have 109 videos up to now in there, which is not everything, but some, I think the first day got already parsed of the conference. And hence, I'm confident that someone feels responsive for completing this list so that somewhere all videos will have kind of a nice extra independent YouTube video. But as of now, this is not yet complete. So I still have kind of the links with the timestamps to the day-wide sessions. And then there's the GitHub link to the package. So this this package I liked a lot. I'm not into graphs so much, but graphs are always easy to comprehend. And this is a method to do approximate graph algorithms. And it's especially easy to comprehend. So first the motivation here, again, some screenshots. Yeah, so that if you have a betweenness centrality, which you want to perform on a graph, so apparently kind of a, I think this is something you can use for fraud detection or the like. You see that this is not really scaling a lot. And yeah, and a graph of 100,000 nodes is quite common. Yeah, so what is provided here is now a method of compression, which still, as I understood it, okay, so I got kicked out shortly. I need a short feedback. Can you still see my screen being shared?
Yes.
Thank you so much. I was disconnected and I was not sure whether it's still there. Thank you so much. So the idea here is very easily described by 2 slides, which I copied further. So the idea of this coloring, quasi-stable coloring approach is that we have initial graph, then we do a coloring so that we specify certain subsets of nodes of the graph. And it turns out that this coloring, if you have defined it like they present it, you have a subset of the graph by just combining all the colors together. So you have in this right one really just one node per color. So this approach is kind of the basic idea. You simplify the graph, you reduce the size by this. And it turns out if you use their coloring mechanism, then mathematics has shown that if you apply kind of these 3 kinds of things, max-flow, min-cut, or linear optimization, or between a centrality, that the result will actually be approximately the same. So this is pretty magic. Hence, I loved it. So I always like these kind of talks, which you can easily comprehend. But some wow, okay, this is a possible moment. And of course, you find more details in the link. But this is an awesome thing, and they also had kind of a couple of benchmarks they did. So how much accuracy you lose and how much performance you gain. And if I remember it right, kind of you have to count like with a 15% loss of accuracy, so about this size, and you get a speed up of 100. So yeah, this is kind of not nothing, but for doing this in a more experimental setup, it's definitely worth the factor of 100, because if you imagine waiting an hour for a calculation, it's really worth it for experimentation if you offer 15% error margin and just get it in seconds. So awesome part, and probably I'm not sure whether this generates to other parts as well, but yeah, it looks somehow that like you could probably also get other algorithms which get approximated by this method. So this is the little approximation here, which you probably haven't seen because I wasn't scrolling down for you. Thank you so much for the feedback. So it happens that if you have this colored graph, or the graph of the colors, then actually, then still the functions kind of give the same result approximately. And you get all the things which I told you, the 100 times speed up. So then the data toolkit. The data toolkit is something which I definitely want to try out. So it manages your data. And I copied first one overview slide because I always find these quite handy. So Timothy Chapman did kind of some work on looking what kind of alternatives are there. I don't know not all of these. So I've heard of DVC before, but yeah, kind of many others I haven't. And I'm glad about this overview. And he decided that no, this is not enough. We need something new, and built data toolkit.jl. And what it is, I think, is best grasped by seeing this TOML file. So next to having a standard project TOML and a manifest TOML, now this kind of is the TOML which describes your data. And so you see kind of also this indentation level. This is, and TOML is optional. But yeah, so it's kind of where it's structured, and you define some metadata, you define where you get it from, and you also define how it's being translated into Julia. And and here it's translated via CSV. And then on the Julia side, I haven't got a screenshot from this. You just do a string iris. You write in the string, and before the string, you use the string macro D, so just for data, and then you automatically get the data. So it will be usually a data frame if you load the data frames. And yeah, this is nice. And there are kind of a couple of further features. So it's really feature rich. The talk's longer than I expected, actually. So you have support for a REPL mode where you can add data. You also have support for transformer pipelines so that if you change some data, everything else will change as well. And you can create new data sets, which are then also here linked here accordingly. You have support for caching and all this. So it's pretty amazing that I haven't heard before of this and that it's already arriving with such a feature-rich setup. I'm not sure kind of how stable it is until, but I guess it's kind of going to be supported very well just because they already spend so much effort in it. And it also looked well set up from my perspective. So I guess it's going to stay there for a while. So I recommend using it from this heuristic. Okay, so next one, completely different field, is a simulation of fracture and damage with peridynamics. This is from Kai Partman. And yeah, I liked it just also because I liked it especially because of the talk. So I'm not into simulation. I'm more the data science person or data engineer even. And hence specific simulations always have kind of the part of being too specific for me. But this one I liked very much. So yeah, the initial motivating example was how does the spaghetti break? This would of course be an all lovely question for the Menti, but I leave it for now. So imagine this, you break a spaghetti and the question is, how does it break and more specifically in how many parts? And I myself was actually kind of naive and thinking it's going to break in two, but that apparently never happens, that it's breaking into two parts. Maybe also this image suggests the breaking into two parts. So it's a little biased. But so after kind of some slides motivating and introducing, he is also showing the simulation of the spaghetti. And yeah, so this is just a screenshot, but of course they are moving pictures. The simulation goes on. And you see that it starts kind of at one part initially, but then the shock is translating to other parts and introducing more fractures. I think this is the technical term. And in this case, the spaghetti is breaking actually even in 1, 2, 3, 4, 5, 6, 7 parts. I'm not sure about the distribution here. So yeah, so it's apparently often more parts, but at least 3. So you don't get it to be just 2 parts. So like that one. There's fuzzy logic. I think something like this was also last year there. I think I wouldn't like it, but I just looked into it and I liked it because of special syntax. So Julia has macro support and you can define domain specific stuff inside Julia. And this one was especially surprising for me. So here they implemented, or Luca Ferranti showed the implementation of a little controller, which is defined by some, this fuzzy logic syntax. And I can't explain the details, but apparently, so you define kind of a couple of components with distributions. So these are these shapes. And then in addition, you can define rules so that if something is negative, and this is a kind of the example of the pendulum. So if the difference is negative, then your force should be, and this is just kind of the opposite. I can't translate it right now. Negative left or something. So it's really kind of pushing it to the other direction probably. And and the same here. And the core thing which I liked is the simplicity. Kind of you have some rule here, and then you follow kind of another state, another rule. It's really more logic based. And I'm not sure about the details how this works because fuzzy logic is of course about probabilities or like something like probabilities, so that you don't have 0 and 1, something is there or not, but you have kind of a smooth transition. Something can be there to kind of a portion. And hence I was surprised finding that you can write such really logic-like rules and still work on the fuzzy part. And yeah, he also mentioned that you shouldn't use something like this to control a real pendulum in production, but at least it worked. So this was kind of this pendulum, and with the plot before, it was really oscillating. And yeah, and now it was kind of stabilized, not perfectly, but still stabilized to stay there. Okay, so next is Just Say It, presented by Samuel Omlin. He's actually going to appear second time in my little list, but totally unrelated. And this is, yeah, I probably should try it, but I guess I'm not going to try it just because I'm lazy, and also I got my tools. But I think it's super fun, especially if you still like to just increase your toolbox. So this is about really giving your custom commands of translating something you say to something your computer does. And it's really meant to be very, very flexible, and as an extension also of a developer. Yeah, so you really want to simplify your life, not the life of an average person where you connect some Alexa to it, but it's really meant to automate tasks for you on your computer. Yeah, and there's a lot to it, a lot of flexibility. And I decided for this screenshot to give you kind of a taste how powerful this is. I actually haven't understood the details why it is so powerful from the talk. It was kind of also introducing kind of other things you can do, but I think it's quite impressive. So you have, if you say letter A equal digits 3, 4 plus letter B, something like this can be passed, and in a flexible manner. So yeah, you have kind of in the first part this command recognizer, which is now letter A. So this kind of directly A. You have the equal, which is also directly translated. The digits 3, 4 is now a digit functions recognizer. And yeah, so it waits kind of for the next parts. And as you can see kind of from the semantics here, yeah, it really needs to wait until you say something different than a digit. So yeah, this is pretty cool. And then you can say plus again, which directly translated, and letter B. So yeah, so something like this is possible. This digits 3, 4, which is in the center, is kind of the amazing yeah, part. So you can build these commands in such a flexible manner that yeah, you can also yeah, build something like this. And yeah, they showed kind of that you can then control your Visual Studio Code or your browser, and it's really kind of to yeah, so that you can make it customized. And what's also special about this, which is not so often being found in the Julia world, is that this uses actually multiple programming languages. So this is not only Julia under the hood, but it interfaces then Python, which then interfaces some other C libraries. So the goal here is definitely not to make something kind of super Julian, but to get something to work. And yeah, I also like this attitude. So I think here and there it's really useful. And yeah, and this seems to be a powerful tool, which could be a tool of your toolbox. The next one is a pre-recorded call, actually, only mentioning it shortly. Vahana, a framework for large-scale agent-based models. The talk itself was a bit dry for me, still awesome to hear, thanks to Stephan first. I think from Berlin, actually, also not too far. And I wanted to mention it because we had kind of the agents.jl being presented at Julia User Group Munich. And here kind of a new agents framework is built up from scratch because of performance and especially scaling demands. So yeah, if you have agent simulations, then this is worth checking out definitely, because they thought a lot about it and decided to build a new package for it. Next is one of my favorites. Actually, this is also pre-recorded talk, sorry, and I haven't seen it on the conference hence. And actually I was getting to know it beforehand, but still it's super new, and I really love it. So I'm also taking in a moment why. So Dimitri Bargev was introducing this, and I just copied one slide, which is also yeah, with not too much on it. So this is a little comparison, and this is also like how you should think of RX infer. It's really like a Bayesian inference system, which is meant to be as complete or almost as complete as Turing. So if you go to their webpage, the rxinfer.ml, then yeah, then you really kind of see tons of examples. And it's hard to kind of tell what is really now the difference. But yeah, they made this slide to clarify the difference. So rxinfer is really intended to be fast. So yeah, it has a message passing algorithm under the hood, reactive message passing, so that you can build a super quick Bayesian inference, and also in an iterative manner, so that you kind of learn continuously. While with Turing, the continuous part is really tough. Takes a lot of extra computation and unnecessary computation because it's just not meant for this case. But it has this general purpose, this general static Bayesian inference modeling. So you have some given data which are just fixed, and then Turing is kind of the perfect tool for you. And it's also supporting kind of everything you can wish for. And Turing actually also to highlight this is one of the packages in the Julia ecosystem which early on decided for stability. In Julia, you have many packages which are kind of still developed and being continuously developed. And yeah, and this sometimes kind of is a bit annoying for people who would like to use it in production because then something changes and breaks. And Turing is one of the packages who really decided for stability. And you see it also in their page, you see it kind of in the interfaces. So Turing is one of the best supported Bayesian inference package in Julia. And I think it's really for this reason that they decided for stability. I like it very much. Yeah, so why I looked into RxInfer is because of cloud.jolin.io. With this deployment of Pluto, I also created a couple of example notebooks, and in one notebook I wanted to have an online version of Bayesian inference. And looking through kind of the available packages, I've seen that this doesn't work, and then out of a sudden RxInfer popped up to my search, and it just solved it. It's really built for this purpose, and I'm very happy, and I'm now combining it with Pluto reactivity to do the online part, which worked. Okay, next a little section. It's just a tiny section of 2 talks. Type inference is the topic, and yeah, so there's one talk from myself. Stephan Sahm, that's me. And I've given 3 talks in total at the JuliaCon. And this is my favorite, and I think the most interesting, most valuable contribution to the ecosystem. Subtitle is Maintainable Type Inference. And yeah, to only copy a couple of the slides, there's actually a very tiny type inference anomaly, which you can currently find in Julia. And this is if you have a vector of an int. So yeah, just nesting a vector in a vector is already in some way so complicated, or yeah, just an exceptional case, that the standard Julia inference cannot cope with it. And if you take a minus on it, then yeah, the inferred type is actually any. So what you see here is already kind of a helper from the isDef package. It gives you an isDef to check whether something is defined, and it gives you an out function to check the output type of something. And the key thing here now is that in addition to some code generation, which gives you nice defaults, you can also override your type inference in case you experience kind of some problem like this. So, and here the method you override is actually not this itself, but a special version of it where you input a tuple type. And we override this case now by dispatching on the specific tuple type. It's kind of the type of the entire signature. And yeah, the signature starts with the type of the function. That's the minus, and has just as the argument, the only argument to the function, just a type variable here, and then we specify this type variable, that it's actually v is an abstract vector of an abstract vector of a number in this case. So this is really just a normal standard type dispatch, multiple dispatch in Julia, and you can define your own rules, and then we return kind of the type. And after having this function, we actually can check, and now the inference works, and it also works on compile time. So this little rule here is completely perfectly valid on a compile time, and this gives you kind of the possibility to work around type inference issues if you experience them and if you kind of need them. It won't fix Julia's internal type inference, obviously. Yeah, so it's still kind of Julia itself. This will not optimize this part. But for a couple of things, this is still helpful. And one application, let me add this to this part, is traits. And I also kind of explained this application in more detail, motivating it, how you would do it differently. And yeah, having this package now finally is kind of the missing step to really use where traits, which is another package of mine. And this allows you to have a very flexible syntax of defining trait functions. So this is it actually here. If you see this traits macro, you just have a normal function definition where within the where statements, you can use additional statements, namely function calls, for example. And the typical function call, which you now get by isDef, is actually this isDef, which is short for isDefined. And you check whether a function is defined for this values or types, actually. So yeah, the value call is super handy for exactly this traits application. So you just check whether element type is defined on this X and the length is defined on this X. And then, yeah, it's like a tiny example, this kind of the iterator interface, which we are checking, not via the traits methods, but by directly checking whether the methods themselves are defined. And then we can use them safely, so to say. Yeah, they are really defined. Now you can also put this kind of into another function, yeah, which just is a check, like a normal Boolean, a normal predicate function which returns a Boolean. And yeah, and then you can check, yeah, let's make a check or is iterator, yeah, and you have all these parts which you want for an iterator, or is an iterator with length or something. So it's a bit different approach, yeah, than the standard traits approach, and the idea is to reduce as much boilerplate as possible. Yeah, but you can also use it just to define kind of what you want for a trait. And then this works, and you can extend this. You can actually also extend this in other packages. So I felt, okay, as always, it's hard to summarize the package in only a few words. But yeah, so I appreciate this work, and I was also happy to have a large audience and could share it with a lot of others. There's another package about types, which I really liked and made a very tiny case, but a very impressive one. And title is When Types Instability Matters, from Theo Gali-Fargeau and Cedric Belmont. Sorry for the pronunciation. And yeah, and this is the example. So yeah, maybe just another look on the title, because it's really interesting actually. And the title is When Type Instability Matters. So this is actually really about introducing type instability for the better good. And yeah, and the case which they had here is that they generate a lot of code. And in this example, this tiny example, they generated a lot of animals. animal types, like a giraffe, a lion, a dog, a cat, a duck, whatever. And yeah, the motivating example is that they want to sort them by coolness and have kind of some logic, some methods around it. And it turns out that this was super slow because of some pairwise functions, and so you're comparing the coolness of animals, and you get kind of complicated parts because if you have kind of a new animal type, everything will be regenerated if you have this new type because of Julia's just-in-time compilation. And this just takes a lot of time. And if you produce a new animal type, it's again kind of recompiling everything. There is kind of an approach, we're going to look into it. So standard Julia has this unspecialized macro, but this only works for your methods which you own. And it turns out that it's really not the main part of the compilation is done in their own code, but just in some base code, which you cannot easily, or you cannot tag this in any way. So you need to live with it. And they come up with this workaround, which is awesome to see. So they have a little wrapper around the animals, which is an explicitly unstable type. So this is more like an any if you want. There's a beast here, which is just kind of just a plain wrapper, which eliminates the type reference. And if you get the coolness of this one, you just get the coolness of the inner animal. But now kind of this dispatch of this animal type is really only confined to the coolness. And all the other methods now see this animal type here, this animal wrapper type. And hence you don't need this pre-compilation again and again. You don't trigger compilation all the time, but only for the coolness part, which is kind of fine. And they actually copied a second slide here where they evaluated the times. And this is really impressive. So by introducing this type instability, by introducing this any, they get an increase of over a factor of 10. So they really compared also the standard Julia recommendation for such cases, the no specialize, and it turned out to do almost nothing. And and same for the second run. So this is kind of a pre-compilation happening, and this is kind of again pre-compilation happening on these because there are some other types involved. This is how they argued for this. And you see that the other one, despite it's kind of only any used, it's still benefiting a lot from pre-compilation. So it's blazingly fast if you want. So it's a really awesome lesson to understand like that it's not always a benefit to have this type compilation, the specialization happening all the time. But sometimes if you have a lot of types, it can be really handy to get this this type instability in there. And to make a final point on this one, so I think the most common or the most well-known standard type which follows this procedure is actually the expression type. So if you've ever looked into it, the expression type, which describes Julia's own syntax, has actually also any's in the type definition. And this is 100% intentional. So this is the same effect. If you have methods which work on expressions, you don't want to compile specific versions for everything, but you just want to compile it for the generic and flexible expression type. That's the very same procedure. Okay, so going on. Symbolic regressions. This is a part which just popped up 2 times, and it seems to be that people really like this. I haven't tested it a lot. One tiny example I have tested, but people like it as kind of a generic way to get an interpretable machine learning model. This is also the title of the one talk, which I can recommend looking at. It was just kind of well made in terms of entertaining. And so from Miles Cranmer, I just copied his his top level, his introductory slide. So he's really kind of using an evolutionary algorithm. This seems to be the standard in symbolic regression to get the syntax tree. I'm sorry for the blurriness, but I couldn't get a sharper image from the videos. And yeah, still it's sharp enough to be viewed. And then it's approximating a function, and apparently a square function here. You see that at the end it's still kind of doing something. I'm not sure. It's just an example, but yeah, it has a lot of clever heuristics how it can do this evolutionary algorithm in an efficient way, and probably even parallelize it. To note, because it may kind of be not so obvious, there's actually a second package out there which is doing the same. That's called Sole or Soul. I'm not sure. Probably this is French. Soleil. Don't know. And yeah, so from Giovanni Pagliarini, at least presented. And last year at JuliaCon, there was actually another related talk about the high-level package around it, or this application around it. So they built model decision trees to have a kind of a decision tree which can also work on audio or image data. And this is the underlying symbolic learning system which powers this. Yeah, so good to know. And yeah, it's also good to know that there are already different and very well supported versions. So I can't recommend the one over the other. I haven't tested them extensively, but it seems like this approach of symbolic regression, many like it. So if you do some machine learning, you may want to try it out as a baseline or something. So the general advantage these symbolic regression models have is that they usually generalize better, and of course are interpretable, or better interpretable at least. Another section is about geometric algebra. It's the same. There have been kind of two talks, and here actually one after another. And it was the first time I was introduced to geometric algebra. And hence my focus still is more on the application side of things. So the first talk was by Cedric Belmont, and he has a slide about the applications, which I copied to you. So robotics and computer vision apparently use geometric algebra, computational geometry. Okay, I think this is rather a research field, but still game engines, space-time physics, electromagnetism, and more. And the general idea, I already wrote it, but I haven't mentioned. So this geometric algorithm seems to be the generalization of rotations and projections and all these geometric parts. So in a sense, also it generalizes complex numbers, which are there for 2D rotations, if you want, and quaternions, which are there for 3D rotations. And yeah, it gives this to higher orders as well. There was also a second talk from Chris Doran. I also liked this. It was also very easy to comprehend. I mean, not completely, but it's kind of this combination of something which you feel like, okay, you can grasp this more or less by hands because of this geometric part, and also kind of have the link to software in a very concrete and concise manner. And unfortunately, this GitHub repository doesn't seem to exist. So I'm really not sure. It seems like there's currently no way to access this source. I don't know what's going on there. But still, there was a reference to some papers which use this. So it's for example here, geometric algebra transformers. So it's also used in neural stuff. And here and there, I also like to see kind of the new advancements of neural network architectures. And and there seem to be two references to this. Let's see, maybe I will find time to check them out as well. So the neural papers are often very high level. I like this as a not too deep researcher, so they are often easy to read. I continue with some neural network stuff. And here I start with a talk I also have seen in person, the Robust Neural Networks talk from Nicholas Barbera. And it was really impressive for me. I heard about something like this already years ago. Now it's in Julia. I'm not sure how much of it's kind of I say older mathematics, but still I don't find many who use it. So yeah, it's about having neural network cells, neural network units, which self-adapt in the sense that they have robust feature. They have kind of self-improving features. And the most self-explanatory slide I took out of this is this one, an example application. So he also went through theoretical details. Example application on robust reinforcement learning. So these are 3 lines, which are very easy to grasp. With the baseline, which is the one which we actually, which is kind of the optimal procedure, inferred just by analysis. And then we have 2 different learning approaches. The green one is kind of the standard neural network, so which just uses a standard gradient descent. So it's called feedback over here, but I think it's referring to kind of the standard neural network. And the yellow line is this preferred robust neural cell, YOLA. Yeah, that's just the name. And we see kind of also the explanation. So if they start, they are kind of similar because this was the training data they've been trained on. So this is the reinforcement learning part of a robot, in a sense, or some machine. So it was trained, let's say, kind of on 2 seconds or something. Yeah, so the unit is not given here. May it be trained on an hour or something. Yeah, so still. The robot itself is going to continue using his algorithms for all the time he's out there. So 2 hours, 3 hours, 4 hours a day, 2 days. And yeah, and this is then a part which was never trained on a classical neural network. And the more you get away from the training data, the more you have some abnormal behavior. And then this example here, it's just kind of, yeah, going somewhere. Definitely not the stable version. I'm not sure whether there's some real data on that actually, but you get the idea. And the robust neural network, yeah, it's really self-adapting and can be used for these tasks, where by nature you just have kind of a limited data set, but you want that it really extrapolates to a lot of more data, in the sense, yeah, extrapolates over time. So this is awesome that this is there in Julia, and yeah, looked really good with some awesome applications. Yeah, see, I also made a second screenshot here. This is because I myself I studied applied stochastics, so I'm into probability theories a bit. And yeah, this is more complicated, but yeah, the summary is that if you kind of want to estimate the dynamical, the state of a system, like if you have a pendulum, yeah, or like this normal pendulum, but you only have images, and you want to infer kind of the velocity and the angle, so the 2 states of the system, by looking at the images, then this is kind of an advanced application of a Kalman filter with some nonlinear transformations from the image to the actual dynamical system. And it seems like, and this is pretty impressive, I actually would like to know more, that using these robust neural networks, so concretely the name is this contracting models, you get some mathematical guarantees that they really converge to the right state, so that they actually get it. And I'm not 100% sure, yeah, how stable this is, but yeah, this is kind of, yeah, the example which is explicitly written here: estimate position velocity from camera sensor. And yeah, and it's something in this direction which many have tried, and I think also many have tried it successfully, but this seems to be a very mathematically sound approach to this. And hence I like this very much, because it out of a sudden connects to something where I rather know about probabilistic models which do this. Okay, so last part about the neural networks. Let me check the time. Whoa, I need to speed up. Okay, so exploring synthesis of flexible neural machines with Zygote. That's an awesome talk. I was very impressed. So from Michael Bukatin, also called Mishka, or calls himself Mishka, he was speaking about flexible neural machines, which somehow have the possibility to learn themselves in a really literal manner. So standard neural networks, they kind of work on scalar values and matrices. And these flexible neural machines, they work on scalar values in trees, in labeled trees. And with this, you have kind of more flexibility, and you can somehow, get the neural network itself into the neural network so that it can learn it. It's, okay. So this is a bit magic, and I haven't understood it precisely, but it really sounds like, okay, there's something here. It may need another example or another look into the mathematics, how it's really done, to understand how it's really doing it. But yeah, it's a kind of an impressive application, and also gets this Julia feeling of having kind of a very individual combination of parts. And then this kind of neural networks, which work on trees, and then having automatic differentiation on them. So yeah, some 2 slides which I took, some comparison transformers, you may have read it now, and then a concrete example that they synthesized a specific machine, a specific state machine with different parts automatically. And this was the magic part. So right-hand side was the target. This should be learned, and left-hand side is what was learned. So it's still kind of not exactly the same, but it learned something. And and the big question is kind of how it's learning this structure actually. But it seems to be part of this idea that it can learn the structure. They are looking for collaborators. So if you like this approach, check this out. So yeah, exploring synthesis of flexible neural machines with Zygote. I have a last one actually for neural parts. And this is nerve. And this I just want to show you by video. So this is a real-time neural 3D scene reconstruction. And the best part is to kind of see its effect. Unfortunately, you need a GPU from this. I'm not sure whether you can hear the sound of the video, but this is apparently, a 3D representation of the author, which is done by this package. So you have a video stream or only pictures. I'm not 100% sure what's the input because it's not described in the video, but the package is there. And this is now indeed a case of a pure Julia package, which replicates kind of something which is already there in other ecosystems, but in a super nice, concise, easily to understand way, which then also is very performant. So this is a standard Julia example of something which is really awesome. I unfortunately don't have the GPU on my machine, so I can't test it easily because this is apparently needed. But yeah, so if you have a GPU, I recommend you check out this nerve example. Okay, so I have half an hour left, and still some things to do, good to go. But okay, we are more than, we have 2/3. I think this looks good. The next big section I want to show you is about high performance computing and also special hardware. So this is kind of one of the big fields of Julia, hence super interesting. But it's also kind of one of the fields of Julia where it's not yet there where it could be. So there's especially in the special hardware part, there's one about Arduinos. Yeah, it's not so easy. So compiling static C code is one of the big challenges. We come back to this also with a summary of the state of Julia at the end. So first package here is from Carsten Bauer, and it's about pinning Julia threads to CPU cores. And this is something which apparently can optimize your code. So if you're not into super high performance, this may not be so interesting to you. But still, I found it kind of very interesting that some functionality like this now exists. And it was also mentioned in many, many other talks. Like, yeah, I was attending the high performance computing section, which went over a couple of hours, and thread pinning was often mentioned as one way to improve performance. And this is now here one screenshot where he mentioned one compute node, the AMD EPYC 7763. And this Zen 3 is kind of one of the cores. And then they have a kind of a shared cache, and then they have a shared NUMA domain. And this was the very first time I've seen kind of something like this, but I heard these words before. So apparently this L3 cache and the NUMA domain are just details of how a CPU is structured today, or in general a compute node. And these affect your performance. And with thread pinning, you can kind of say, okay, I want to have them at the same cache, or I want to have them at the same NUMA domain, and you can control this, which then affects the communication between your cores and then can speed up your entire part by actually something like a factor of 10. So this is really decisive. I'll skip over the effects. It's probably quite detailed, but I have a special link to the parts. Another talk is about the Intelligence Processing Unit, or short IPU. So this was just also an awesome talk, very interesting. And it's also one application which apparently many Julia developers are proud of, that this is possible. So yeah, Julia is one of the first which is really kind of being deployed to this special processing unit. And you see here, I copied, so thanks Mose Giordano for this work. And yeah, I copied one slide here where he had an overview how to imagine this kind of architecture. And we have the standard CPU, which is designed for scalar processes. So we have more or less one process, which then access the memory. Of course, we have multi-threading today, but still kind of this is the basic idea. And in the GPU case, we have a single instruction, multiple, now I'm lost, data, I think, architectures. So we have a single thing which we apply on thousands of different data. So this is the key part, the GPU design. And the intelligence processing unit is now more flexible than the GPU. This is a multiple instruction, multiple data design. So yeah, you don't need to have the same instruction run on all the data, but you can really kind of have different instruction on different data, but you all run them in parallel. So the parallelism is still there, and this is also the key difference to the CPU. So it's definitely parallel, and yeah, and you don't have the sequential part which the CPU gives you. This apparently kind of also comes with some further difficulties, like having more power also is a bit more difficult to address. But I copied this slide. So the general approach is always like to have it use the GPU compiler package, which was developed mainly for GPUs. But this now compiles Julia to some specific code via the LLVM intermediate representation. And then this one can somehow be put to the IPU. I don't know the details, but yeah, so somehow this works. So the key part here is always the GPU compiler.jl, which seems to be the magic piece, which is already quite advanced by many people having worked on it in the GPU case, and you can use it also for other architectures. And the second example is the Arduino, where Valentin Bogart presented his part. I have a little summary slide here where he warns about this. So this is really experimental and not really supported in Julia. And it's kind of the same case as with the IPU. So this is also experimental and not yet supported. But yeah, so still kind of it's one of the fields in the IPU case is about massive parallelization. For the Arduino case, it's about really kind of low resource environment and an embedded environment. And they here also kind of gave a little example about how this actually works normally. And it's the same kind of, this intuition also applies above for the intelligence processing unit. So the normal Julia part is that you have kind of some syntax, you parse it, you lower it to some lowered representation, you do type inference, you optimize the intermediate representation, you have the LLVM compiler, which again has another intermediate representation, does further optimization, and then you have the actual runtime, so the machine code which is executed. And the normal Julia, this can now call other type dispatch or even maybe even evil, so that you have new code constructed. And if you get into another environment, you have to cut out everything else. You only can use the runtime. All the other parts, they need to be kind of cut off so that they don't happen at runtime. And also you do need to care about this compilation part just before. That can't be done on the final machine in this Arduino case because there's just not enough resource on it. And here again, it's the GPU compiler, which is the magic piece, and a wrapper is written around it, the 8VR compiler, which now has this Arduino support in some way. But no, the warning is there, it's super experimental. And he gave a little link I'm going to check out, cpu.land, where you can understand a little bit better how such computers actually work. This is going to be my next tutorial, which I want to look through. So yeah, computers from the ground up. Still in the high performance field, there was a talk by Ludovic Ress and Samuel Omlin. So we had another part of Samuel, but this is really now completely different. And I just want to mention it, I also attended the workshop. So they have a talk and a workshop about the same thing. And it was pretty impressive to see. So they kind of had automatic differentiation through a super big model, which they run on multiple GPUs. And this apparently is a new field. Yeah, so this was not easily possible before. And they did it kind of with some extra work on their own, definitely. Also, kind of one part of the differentiation is done manually for optimization. But then, yeah, they are also using automatic differentiation with enzyme on GPU kernels, which apparently works. And then they parallelize this on multiple GPUs by using some grid approach. And yeah, and this works. So this is pretty advanced and also combines kind of this auto differentiation with the accelerators and the parallelism. So yeah, really excellent Julia example. I also wanted to shortly mention Julian Samaro with the talk about Dagger. This unfortunately a little bit hidden inside the HPC talk, the high performance computing section. There have been a couple of talks which were not mentioned explicitly on the schedule, but then just inside this little mini symposium. So there are a couple of new things in Dagger. If you don't know Dagger, this is really kind of for the beginners, the easiest place to get started with high performance computing. This is meant to be super easy. So you just have a spawn macro and the rest is taken care for you. And yeah, and there are kind of some further supports being added. So the MPI interface for an MPI-based cluster, if you don't know, don't care. There's also support for the folds, Julia folds infrastructure, so transducers, and this come in here. They better supported. And GPU support is now also going to be added or already in there. So they're working on it and improving it, and it's really kind of the goal to make this the standard go-to interface for high-performance computing. Just one macro, spawn, and everything else should work. So at least kind of the rough idea. I like it a lot. Yeah, so I hope that Dagger is going to be the alternative to Apache Spark somewhere. So if not today, but yeah. So this is my little dream with Dagger. Let's see. Yeah, I also want to mention Jack as the last part on this high performance part here. So there's kind of the question, if you go to these high performance accelerators, that you would like to have a somehow good abstraction layer, so that you don't need to write code for the one GPU, for the other GPU, for the third GPU, and so forth. And then there are also these other processors which may come up with, like we heard, the intelligent processing unit, the IPU, and and this is apparently still a field which is not settled. There are different approaches. And Jack is now one talk which was there on JuliaCon, which targeted this topic. So they presented one way of having an abstraction, which then can be used on all these different accelerators. Some alternatives there, also kind of the oldest one is the kernel abstractions, but this is a bit limited apparently. So people want to have something more, like Jack, for example. And what was also mentioned, but there was no talk about, is apparently also a little bit older. That's the parallel stencils, or maybe it's newer and there was just no talk about it. I'm actually not sure. But this parallel stencils, this was actually used in this multi-GPU auto-differentiation case. So this super parallel, super accelerated example, they actually used parallel stencils. And so this really seems to be a thing, that you want to have your code written in a way so that you can test it on your little notebook, in a threaded environment, but also use the same code to put it onto multiple GPUs. So this would be the vision. And it's not super simple, but there are kind of some approaches to do this. Quantum. Okay, so this is the last part before my final state of Julia, actually. So the summary of quantum is that quantum is really huge. So I was surprised by seeing so many quantum talks, and I felt a bit stupid. I should do some quantum lessons. So most of the talks are, of course, in the field, and if you're not into quantum, it's probably hard to understand what's going on and what's kind of the nicety of it. But I heard that it's not so super difficult. But definitely a little learning curve. So hence a high level. So the first talk is more or less actually chosen because it stands for quantum being really huge in Julia. And this is namely AWS investing in Julia. So there's bracket.jl, which is which is by AWS Labs, and and supporting now Julia, experimental still, as we see in the auto GitHub link. But still, so this is a big step. I'm not sure whether it's the first, but somehow for me it's the first time I hear that one of these big clouds is actually investing in Julia. I think I've seen Microsoft also being here and there with some Julia parts. But this seems to be a big thing. And then I kind of made a little other talk here, which I find kind of nice also in the presentation. You see these nice Julia colors, which is about symmetries and tensor operations. And they also gave a little introduction to tensor operations itself, so that you can write some summation rules with some einsum notation. Just putting it here because I like the colors and the notes. So they really took care of some nice design. And then the really thing of this one was that they presented this symmetry helper. I'm not into it. I'm not sure actually, but it sounds like awesome. I did some group theory back then in my academia classes. And yeah, so symmetries can be represented by different kinds of groups. And these are them, I guess. And yeah, and having this support, they somehow can reduce the complexity of their models by enormous factors by just kind of applying the symmetries to the problems and then reduce the parameter space a lot. And of course, everything is much faster if you have less parameters. And especially in quantum, this seems to be super important that you can use every optimization, every efficiency which you can, and symmetries are apparently one of them. Okay, so I'm sorry that I have such a few time for questions in between. It's always hard to assess how long things take to present. I think for the completeness to get there at 8, I just go on. And if you are willing to stay with me longer, I'm happy to stay with you longer and answer some more questions afterwards. So that's the last section. It's a bit longer again, but not too long. That's the State of Julia talk. So yeah, that's kind of the most interesting of the conference. Everyone is waiting for this one. And yeah, the State of Julia talk had this nice overview in the beginning, actually. It was rather in the beginning. So I think this is a really, really great summary of where Julia stands right now. So you see a couple of check marks here. The first two are green. The second two are yellow or orange like, and the last is not yet there. So yeah, so we have an easy installation. This probably refers to Julia Up. We have fast, simple, robust package installation and management. This is the package.jl, which I also very much like and appreciate. Since 1.9, and this is a new kit in the room, yeah, we have fast startup and low overhead. So you need pre-compilation time, which still is some time. But if you have just a laptop and you're experimenting, then this is not so much. I mean, you need every time you upgrade your packages, you have to pre-compile them. But actually, I agree, yeah, that this is definitely another a scene now like it was before. So having now almost all of the overhead in this pre-compilation step, which you need to spend if you upgrade, yeah. But this is similar in other languages. If you upgrade packages, you need to download stuff and yeah, here and there pre-compile things. And it's still reasonable in time. It's not that you need to wait for 20 minutes for something to pre-compile, at least not in my case. And it's really blazingly fast now since 1.9 to use it on the fly, to using packages and then yeah, use part of the packages. And yeah, apparently this increased even more in 1.10 and it's yellow, so they expect even more improvements to come. And it's really already very awesome. There are parts of easy to learn. So I also think that this one has a lot of improvement still. So Julia is easy, but the infrastructure around it still has a long way to go. So I'm here and there myself a little bit surprised, negatively surprised by the state of the development environments. And yeah, for many it's probably working reasonably well, but I expect more. And this is also part for me for the easy to learn, and hence this is a bit more yellow for me. And last part is easy to deploy, and we already spoke about it with the Arduino case. So this is really kind of a thing which many hope for. Me myself as well, and yeah, so that the part to having just Julia being there as a C library, which then can be plugged into other languages easily, maybe even your phone. Yeah, this would be awesome. This is just still very difficult. Or maybe not super difficult, but yeah, with drawbacks. Yeah, this is just one example, which was really kind of a shining case that Julia can reduce the lines of code impressively. Some array stuff here, skipping over it. This is the plot about the reduction in time to first load and time to first doing anything or doing something with different packages. And yeah, this is really impressive. Wow, this is 1.9, and 1.10 even got a little better, but the big jump is really with 1.9. So it's a completely different user experience. So share the news. People should really try out Julia now. The 1.9 makes it so much more pleasant to use. To get the most out of 1.9 for you, take a look at precompile tools. This is the thing with which you can easily construct some commands for your package so that the right thing is precompiled. It's super easy. It's really, there's not much to do, but yeah, without it, your package won't benefit from the precompilation. Another new thing of Julia 1.9 is package extensions. Maybe you now require JL. This was always such an experimental state, and now Julia supports like interactions with other packages built in by default. So this is always the case. Kind of what if you want to only have a single some utility functions which just work for the combination of your package and another package. So very typical one was GPU support. Yeah, what if you don't want to include the GPU support for everyone because there might be someone's using AMD processors or Intel processors. And yeah, and this is now easily done with the package extensions. So also a long-wished feature. And what's a bit tiny mentioned, but I want to highlight is that that's Julia syntax, which is a new parser, so that you get better error messages if something goes wrong. And I also hope that having Julia syntax there is going to improve the state of our Visual Studio Code IDE, especially the language server and some auto-completion, so that, yeah, a lot of things just work a bit more like you'd expect them. And one thing which luckily now works more like you'd expect it is tab completion. And I want to highlight this because, yeah, whoa, finally, since Studio 1.9, you're in a REPL, you have a dynamic object. So in the Python world, this is relatively standard, kind of. Python just inspects the objects, but yeah, Julia, apparently this was not so easy. I'm not sure what was kind of taking this, but it seems to be some inference was needed. And yeah, and now you have kind of standard tab completion on the fields, which is nice. Okay, static compilation was mentioned. Yeah, this is kind of one slide about this. So shipping Julia code without shipping the Julia compiler, you've seen it in the Arduino case. And this is kind of the summary of it. So that there's the plan to do this with Julia. And one big thing, I found this very interesting, maybe you too, is that there's kind of a big choice. And this is the question whether you want to also ship the Julia runtime. Memory allocation, garbage collection, runtime dispatch, task, all this is done in the Julia runtime. And in the Arduino case, you probably don't want this because it's just too tiny. And in the IPU case, the intentional process, you may also don't want this because it just has a different execution environment and the garbage collector just may kill it. So in this case, the static compiler and the GPU compiler, as mentioned, they are more the way to go. They already exist and go this route. But Julia in general wants to be also compiled like as a package, that you can ship your package as a dependency for other languages or just as an app. And in this case, of course, you have memory. Yeah, you have a normal machine and you can easily ship the Julia runtime. But you should ship it kind of in a in a way which is easily portable, which would be a C library, for example. And this is kind of the way where Julia is going to do. And let's see, yeah, this is the hard. Yeah, this is almost the last one. Yeah, works out. So, and there are kind of now two perspectives here. So an easy part of this problem to ship Julia code, and the hard part of this problem to ship Julia code. So the thing is that Julia kind of has this runtime dispatch, and sometimes it is needed if Julia code is fully inferable, so that the type inference just works out seamlessly. as you've seen above. Even for some cases where you think type inference should work, it doesn't work today. But in case it should work, then you just can kind of really compile all the functions you need for your case, because everything is known. You really know all the branches your code takes and all the specializations you need to take. And in the other case, if you don't know kind of the real branching, but your inference is saying up, down now the type, this can be any, you really need to make sure that you get kind of all the possible specializations which could be called. And this list of what is kind of possible, this is kind of a tricky thing. So because if you imagine, okay, should I now specialize on all kind of arguments, and if it has a splash or so, should I specialize on really kind of all types which I have available in all combinations? Of course, this doesn't work. Yeah, so this is combinatorial explosion, and there needs to be some clever way to somehow reduce the space of finding the right specializations. This is the hard problem. So there seem to be some ideas how to approach this. This combinatorial part, this sounds tough. But yeah, so Tim Howley was presenting this, and he was kind of optimistic that at least something useful can come up within, he hasn't named a time frame, but I guess kind of until next JuliaCon. So that something on this will be done. But with all of these future projections, they are very fragile. So let's see. So this little plot is kind of a visualization of how often this hard problem occurs. And this seems to be very often. So he was mentioning a bit more what this graph actually depicts, but the conclusion is kind of the most decisive. Most of the code is actually not reachable via inference, but it's really this hard problem. So it's, this hard problem is unfortunately rather the standard and not the exception. Which kind of on the other side is impressive that Julia gets this speed, even though it has still a lot of dynamic runtime dispatches in there. It's still, being compatible in performance. But so this shipping is really hard, having so many runtime dispatches. Okay, the very last thing I want to show you is kind of a slide also from the State of Julia talk, which gets this famous black hole image back. You may have seen it. So I knew about the first two iterations. So there was a black hole image where they worked for 1 week. And as you can imagine, someone who saw this and got access to some supercomputers thought we can do better. So the Julia plus enzyme version then was getting this down by probably a factor of 100. I'm not 100% sure. Oh no, it's also a cluster. So it's probably a factor of 1,000 at least. One thread for 1 hour versus a cluster for 1 week. Yeah. And then they improved it, and that was kind of nice to see. So they just kind of made a larger picture, and that's pretty impressive. Yeah, I actually am not a physicist. I don't know what's depicted here. I mean, a black hole apparently, but more than that, I don't know. So using the complexity, they now run for 2 days, 8 threads, and have an awesomely detailed picture. Okay, so very, very, very last part, I want to mention that Julia is actually also getting one other part nicely. It's a bit kind of, might not be related to your part, but I'm into functional applications of Julia as well. And for those of you who are also interested, there's a ticket which just got closed a couple of days ago. And and this is like indirect recursion, which was not supported by the type inference before. And one part at least of the problem was fixed. And I'm so surprised and so much looking forward. So this may now be kind of the advent of more functional parts of Julia. Or yeah, at least these parts which use double recursion, indirect recursions, and in a functional style, you have a lot of recursions. Okay, this is my little extra on top. Very happy this got closed and looking forward for the next Julia version which has this. Back to the black hole image. So yeah, then thank you for being there and staying with me. So we filled 1.5 hours compressing a full week full of a lot of things on JuliaCon. And I'm happy to share this with you. Thank you for staying here with me. I'm also happy to answer more questions.